Yeah, hi guys. It's me, Rishi, and Will, our team, and we throughout the semester we got inspired by the second lab where we made the Boyd's algorithm, and we really enjoyed the fact that we had these certain parameters that we controlled from the outside, but there was a certain degree of randomness that the PIC generated, and it allowed us to see patterns and movements of these voids on the screen that were very pleasant or surprising even sometimes, right? So we wanted to do something where this element of surprise remained, and maybe just not have a visual but like a audio pattern that the PIC generated. So we tried to make a system that we could, from a high level, input certain music to, and it would output certain music that could be similar, not exactly same, similar, and pleasant sounding. So not just random notes here or there. We tried to start with notes, then we added note durations, then we added chords and octaves and stuff like that. So we tried to make it as pleasant as possible. Um, the ultimate aim was that if the person can just like listen to this music and use it for his own creations. Rishi likes to make music, so he was saying that maybe we could just like have this sound like something. I don't think we probably got to that stage, like that um level of music, but I think it's pretty good sounding. So Will can maybe show it. So we use a bunch of MIDI files, train the data on Python, make a bunch of Markov chains, send that to the PIC, and then the PIC uses the ADC, the DAC to generate sound. So maybe Will can show a demo of that.
Yeah, and it's pretty cool, like because you kind of get to you generate the Markov chain with Python, and then you get to explore like what the chain, like the physical chain structure, but like with your ears. So it's like pretty interesting to kind of listen to, like for longer duration to see like where the chain goes. So right now, we actually have it trained on the Turkish march. So one second, let me make sure this is sharing the right thing. Okay. Um, yeah, so we have a train on the Turkish march right now, and then this is basically like the output of that. Yeah, so
Wow.
yeah, it only plays like 100 notes and then it cuts itself off. But this is like, and then when you play through, like individual songs that are loaded onto it, like in like classical music, what we found is that you could actually like hear the different movements of the song, because I guess like the way that we train it, there's kind of remnants of the song structure that get carried over um between our training and the actual transition matrix that's output by the system. So then, like, eventually you get to a state where it just keeps repeating the last note. So there is like some remnants of the older structure of the music that you actually put in, but like it sounds drastically different. Um, some of the constraints that we had were with like memory, and so we decided to split it into like a bunch of different chains, and we actually have like a diagram that we could show regarding this. But yeah, and we also have like um, so like to conserve memory, we have five different Markov chains running, and there's one central note chain which kind of is responsible for controlling all the others, and all the other chains are dependent on the central note chain. Um, and then this is like how we were able to conserve so much memory, but still have like two channel synthesis, um, like different durations stored, and having 48 notes, and uh, yeah, then having 48 notes in our range of playing.
Will, do you want to do we have like the large data set demo that you want to show?
Yeah, yeah, I could load this up while somebody else explains more about like how the system works.
Um,
So yeah, to actually change the songs, you have to like physically copy and paste the different
Matrix.
translation matrices. And then we also have like we call them colloquially seeds, but they're actually just starting state. And we have like different starting states for the seeds and the for the note, duration, and octave. And these are just like guaranteed starting states that we don't start in a zero state. We just can like select one starting state. So even within like an individual song, or training data, there's still many different starting states. So there's like infinite amounts of different songs that can be played by the algorithm depending on which starting state you choose, and then those can be chosen by using
Juicy.
CS. Yep,
Just
and
juicy.
then just C.
No, I'm saying that means juice seed.
Oh,
CS.
okay, yeah.
Oh,
So
I see. Okay.
CS, and then you could just like put in like zero. You could just put in like 50, and then this will just start it at So we only have it so you could choose the note seed, and because since every other transition matrix is dependent on the note transition matrix, then this will eventually trickle throughout the entire system. So
You can notice like a little bit of variation compared to the first time
Yeah.
you played it. And yeah, like just to kind of expand on what Will was talking about, you know, each state is determined by like the two notes before that, the previous note and like the current note, and having these different starting points can kind of, you know, depending on which set of those previous current note, you can get to different points in the music based on probability.
And just for people to understand like how we go from just like random MIDI files to these Markov chains, I can just give like a quick overview of like how the Python works. So maybe we can look at the code later, but I think I can just explain. So we have a MIDI file. Then what is a MIDI file when you really convert it to Python is that it is a bunch of rows. Each row is a unique notes. So you will have one column would be the note, one column would be the start time, and one column will tell you whether it's turning on or off. So like it'll be the time signature and on or off, right? So the way we made the Markov chains is that we traverse through we cleaned up the data a little bit, then we traversed through the whole MIDI file, and whenever we saw a on or a off, we registered the note and the start time, or like the time, sorry, not the start time, but the time, which could be the start time or the end time. And we stored that data into another file called the process data. And process data contained an array of a certain note. So it can be note with the MIDI index of 50, its start time, its end time, and its duration. And then this process data file had a bunch of rows with the notes like note 50 MIDI index, note 60 MIDI index, note 70 MIDI index, and their start time, end time, and durations. And once we had that, we essentially made this huge 12 by 4. So maybe I can share my screen, Will?
yeah, I actually have to restart the computer because
I can just quickly show.
Yeah, Raghav, before you do that though, I can quickly show my screen just to kind of, I know Raghav did a good overview of it, but I just wanted to show what a raw MIDI file kind of looks like.
Okay, yeah.
So it kind of looks like this. They have like this header here, and here it can kind of tell you like how many, because the duration is all in like clock ticks, and that's very subjective. So here they make like a distinction on how many ticks per beat it actually is, and most of this is useless. Here's like a tempo that they'll specify, and then this is the actual important data for us, because this will tell us which note corresponding to the MIDI number of it has been played.
Right. So you can see like there is note on, there is note off, and then there is like the second column is the start time. So 960, 960, 1920.
You can see the notes here.
And those are the note values. Yeah. Can I share my screen now?
Mm-hmm. Yeah.
Okay, sweet. Right. For example, you can see that these are the three main octave the main three main Markov chains we had. And so these are like really high dimensional, right? So like you can maybe see the comments and like see that the note Markov chain, it depends on that we have 12 notes that we are playing, and the note Markov chain depends on the last three notes. So this last index just carries the current note, and it depends on the last three. The octave Markov chain depends on the past two notes and the past two octaves, and then the duration note, the duration Markov, the current duration depends on the last note and the previous two durations. So essentially, I will skip through. This is like a lot of cleaning up the data. But essentially, what we did is that here, for example, you can see that we are indexing into this super high dimensional Markov note matrix. And the way we index into it is that note is given like through some clever like manipulation. Each note is converted into an index, right? And once we convert it into an index, we just index into that huge Markov note array, and we bump up the counter by one, saying that, okay, we have seen a certain combination. For example, previous node being a 30 MIDI index, a previous MIDI, previous node being a 20 MIDI index, and a previous node being a 10 MIDI index. We've seen that combination, and we're going to bump up that counter in the Markov chain. So that just means that, okay, this is more probable to play than some other combination. So if you keep seeing the combination again and again, you keep bumping up the counter more and more, and hence like that probability would increase to play when you actually play the sound. And finally, down here, we're trying to use like a cumulative probability kind of thing. So this is a tactic to save data, to save memory on the PIC, because we didn't want to send 4-byte integers to the PIC. We wanted to send like 1-byte jars. So we limited everything to 255. And so we basically, for each row on the Markov matrices, we add up all the values which is being stored in the accumulator, and we divide by the accumulator and multiply by 255. So the highest counter would be a 255, and then you have sequentially you have lower numbers, and hence also here you will understand what the seed is. So remember, like the seed was the point where you start the music generation, because that has a certainty that, okay, like you can go to a certain note after this. There will be a lot of sequences that will never play any music because they just never existed in the actual Markov note. So all Markov indices that don't have accumulator equals 0 means that they do have certain values, are a seed essentially. So they are rows that have certain transitions. So here we basically make note seeds or duration seeds and octave seeds, and hence like basically we send. So finally, what we send to the PIC is a big Markov matrix with rows that have values from 0 to 255. And maybe Will can just show again what those header files look like so that people can kind of visualize.
Yeah, and then also one more thing that I think we should also add on. It's okay if I share my screen real quick as well.
Yeah.
So one thing that we included as well was like making the notes played in parallel. So how this would work is so how this works is that we basically have like so if notes are detected to be starting at the same time code for the on the MIDI file, then what that algorithm does is it will store all of the notes played in parallel in a matrix or in an array that's stored in the current and previous notes. And that's the reason why we have like the many for loops there, because we're actually looping through each combination of all the different possible states that the system can be in, and then accumulating those values so that the music can still run through in a more natural way without having a bunch of arpeggios in the MIDI.
Yeah, because the problem we were facing was that like in the MIDI files, a bunch of notes would be played at the same time. But the way we had it earlier, if at time step 0 there were 5 notes being played, we were sequentially going through all the 5 and then going to the next 3 or 4 time step 1. But with this system, you can go from note 1 to note 1 of time step 0 to any of the 5 in time step 1 instead of like sequentially going through all of them. So like we just have a bunch of branches from note 1 from time step 0 to time step 1.
Yep, and then I still have to join the Zoom meeting, and then I'm going to play the demo that has like a very large training like training data used to train the algorithm.
And is this this very large set of training data, is it music of any particular variety?
So this is like 100 ragtime songs that we just like scraped off of various databases of MIDI songs. So a lot of them look like they're built in the 1980s, but I think that like about 1 in 5 of them are formatted like in a different way that's conventional for MIDI, because like all the MIDI files are formatted differently, and like people say you'll never know what you find in a MIDI file, and like a bunch of them have different edge cases. A bunch of them store values in them as strings or integers or floats, so it's like different in every single file. But this is the very large training set. So with the larger training sets, it is much less coherent, and we think it just because when you like put a bunch of data into it, it doesn't actually improve the way that it doesn't actually improve any portion of the Markov chain, because like if there's a bunch of songs overlaid, then they might have different chords in like different successions. So then if it just kind of piles them on next to each other, you'll always have a higher probability of hitting something dissonant in each state rather than like actually having higher probabilities of hitting something good. So since those exist and we have like 2 channels of synthesis going on, then that means that like there's a higher chance of hitting stuff that sounds dissonant when you have larger sets of training data. So we found that it sounds better when you're using less songs than using more. Interesting.
And did I hear 2 instruments in that? I heard a string and a chime, I believe.
Yeah, so this is just what we also found is like at different frequencies for the FM synthesis, the instruments sound different. So okay. The higher instruments sound like a more like a pluck string, or the higher frequencies sound more like a pluck string, and then the lower frequencies will sound more like a chime. So it actually kind of works out because like the bass sounds more like the chimes are better for playing bass, and then the pluck strings are better for playing like higher registers. So it actually kind of works out. With
and like, we could also change the instrument though, right, in the GUI.
Yeah, you want to show the different instruments?
Yeah.
Could you change the seed?
What's up?
Could you change the seed also so that we can like listen to a new?
Okay. So and then changing the seed wouldn't actually like it's possible the seed will be reached naturally in the Markov chain, but this is just like a different starting position that we could choose. and this one's my least favorite.
Like
I call it futuristic music.
like Star Wars stuff.
You're muted,
Oh,
Bruce.
yeah, okay, Bruce is talking.
Very cool.
Very
Well, in terms of the goal of building something that's capable of surprising you, I'd call that a total success.
Okay. That's great.
Yeah.
Yeah, I don't think it's like very, very pleasant to, like, this is not this kind of music I would jam to or listen to while walking, but I think it is very cool.
true.
Yeah.
The training on the one song you did earlier was much more coherent.
Yeah.
Yeah.
And
We can also do a. Sorry, I didn't mean to cut you off.
go ahead.
Oh no. I was just gonna say, like, we can also do a live demo in front of you guys. I have a mini keyboard over here.
Yeah.
Yeah, and then also like one thing I wanted to show before we run out of time was like this block diagram of like all the different Markov chains and their dependencies. So this is basically like the structure of all the different chains, and like it's color coded according to like what's dependent on what. So and in which order. So this is like basically what the system's running right now. I think that we could make it sound a little bit better if the channel 2 octave was dependent on itself instead of on what the main
Bill, could you explain like what is happening actually? So what are these arrows like? What is X3, X1, X2?
Yeah, so these are color codings like based on what each of these individual chains are outputting.
Okay.
And then the X1 or X2 or X3 represents the order at which chains are dependent. So this is like what the system is currently. We do have the support for 3 channels, but we found that if you have 3 channels, then you just have a higher probability of playing something that sounds dissonant. So that's the reason why we took it out.
And
Okay.
channel 2 is channel 2 enables additive synthesis because you have different 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 channels running different frequency modulations basically.
Really cool.
Thank you.
You really carried this a long ways. I'm amazed at how much you managed to fit into memory.
Yeah. Thank you. I mean, we really like. I think like definitely like splitting into different Markov chains. I think that might have sacrificed like the quality, but definitely it was like the best way to get around memory. And also with these different like chains included, then we can actually just reuse like the previous chains, right? Because if we're having the channel 2 note matrix dependent on like the previous 3 of the main nodes, then we can just reuse this chain. So we have the second channel without any memory usage. And then since we're doing the chord generation in the manner at which like it's parallel, then that means that all of the next notes that could possibly be played are automatically portions of a chord that were previously played in the music, meaning that this is also would be like an advantageous addition to the to the system, because it's more likely to play like a chord that sounds coherent. And this is probably another reason why larger training sets just sound worse on it, because if like there's 2 songs overlaid, then it'll have a high probability of playing 2 different chords from 2 different songs.
Sure.
So if you take